We can't hear you, Jem. You are muted.
That's always the case, isn't it? I'll start again. Hi, everyone. Great to see you all. I hope you get something out of this workshop. I've run it multiple times now, and people seem to react to it very well. Before we dive right in, let me orient you a little bit to our plan. You should have received a link in an email from me that I believe Abdu will probably post to the chat to this page here. In this page, it has a little intro like why you want to take this course or this workshop. Basically, the idea is this workshop is aimed at people that have done some programming in that R programming language, but maybe not so much work with geospatial. If you have more limited experience with R, you might have a tougher time, but it might be worth it. I also sent out in the email some pre-work. The design of this workshop is meant to be interactive. So I asked you in the email to download some data that's here at this link and install R, RStudio, and these R packages. The first part of our schedule today, for the first half an hour I have planned, I'll talk about some geospatial concepts. We won't do any programming initially. During that time, if you haven't installed the packages or the software, that's something you could do then. So I encourage that. And the idea is that once we get to the interactive part, I will basically be doing live coding. So we'll walk through the analysis of a data set having to do with Lake Erie in North America. And we'll deal with some vector data for Lake Erie and then some raster data from Lake Erie. All right, I'm going to switch over to the background document. I'll just preface this by crediting my fellow data carpentry instructor, Ben Best. And this is the first time I've mentioned data carpentry. I'll just say that all the materials for this workshop have been adapted from data carpentry materials with the same name as this workshop, working with geospatial data in R. So I encourage you to check out data carpentry, maybe consider becoming an instructor. I did. And then we're always in need of help for maintainers of the lesson materials. So check out the data carpentry geospatial materials, consider being a maintainer, consider being a data carpentry instructor. Yeah, as I said here, credit Ben Best for most of the materials in this intro presentation, and then data carpentry for the interactive stuff. I'll be going through some GIS background, talking about projections, which is a key concept in working with geospatial data, and then some geospatial data types. One of the big, powerful features of geographic information systems, or GIS, is the concept of layers. So you might have a roads layer, a hydrography layer, an elevation layer, and the real power is combining them, like extracting elevation according to boundaries, let's say. That's where the power comes in, not so much looking at individual layers, but this layers concept is really key. That's some of the power of GIS. One of the challenges of GIS is dealing with projections, or dealing with the fact that the Earth is not flat. We live on a spherical Earth. So all GIS data is represented in a coordinate system relative to our spherical Earth. In an unprojected system, you're dealing with units of degrees. So that's what this is meant to show here. So keep that in mind as we're working today. I don't think that you'll need any of these terms specifically. I mean, I'll just assume everyone knows what the equator is, but latitude and longitude. So sometimes I know it can be difficult to remember which one is vertical and which one's horizontal. So longitude is a measure of distance in the X direction or the horizontal direction, latitude in the Y direction or the vertical direction. When you combine the two, you get this graticule network. We won't really deal with georeferencing, but it's useful to know sort of how GIS data is created. So people will take measurements on the ground, and georeferencing is the process of taking those on the ground measurements and putting them in coordinate space. We're going to be dealing with several map projections today. So as I said, the Earth is round, and not flat, but all our maps are flat. So in order to make that transition from a spherical Earth to a flat surface, there's some distortion involved. And there's many different strategies to like minimize distortion that might be important to you. So there's specific projections to maintain accurate area, specific projections to maintain accurate like distances within a given area. We're going to be dealing with, I think, mostly unprojected data in latitude and longitude. And that's generally not a problem unless you're working over very long distances. So if you're looking at the scale of like, I don't know, a third of a continent, you'll start to get errors using unprojected data. Map projections introduce some odd visual effects. So one that I think is really notable to me is the comparison between Greenland and the continent of Africa. On one of the common map projections, the Mercator projection, Greenland looks like the same size as the entire continent of Africa because of the distortion involved in going from a spherical representation to a flat map. But if you take Greenland and translate it using a different equal area projection and lay it on top of Africa, Greenland is much smaller than Africa. Africa is larger than a lot of places as a continent, even though it looks small on the map, just because it's kind of in the middle of the map. I won't play this YouTube video for you. It basically emphasizes the point that Greenland is much smaller than Africa, and it goes through some other interesting examples. So one thing you can do is check out that YouTube video afterwards. You can find this link by going here. Maybe Abdu can put this in the chat. This is the link to the slides that I'm going over now. So if you go follow that link later and view this YouTube video, it's pretty interesting. All right, the last topic for this intro material is different data types. So we're going to start the workshop by dealing with vector data. So people might not be too familiar with the concept of vector data. A lot of people just like in common speak, just talk about shapefiles. So you may have heard shapefiles. The shapefiles are all vector. And then we'll end the workshop by dealing with raster data. So that might come in a file extension like a geotiff. And this might not mean anything right now, but I'll go through some examples. So some vector examples, you can have vector data as points, lines, or polygons. I think we're going to be dealing with all three today. And then raster is essentially a grid. So what I have here is showing some polygon representations in vector format, and then those same polygons rasterized to a grid. And I've got this phrase here, rather Ben Best has this phrase that he really likes called, that goes raster is faster, but vector is corrector. And that just means that computation-wise, rasters have the advantage that they're very fast. You have those grid points, computation is easy. The vector data computation can be much slower and more difficult, but it is more accurate. Underlying that grid that we just saw on the previous slide are actual values. So you have the X and Y grid, but then each grid cell has a value. So this might be, let's say, an elevation grid, and each of these numbers is an elevation. Or we're going to be looking at in the workshop some bathymetry data, and there each of these grid cells holds a depth value. There's lots of uses for rasters. Land use is a big one in limnology, but also elevation, bathymetry, that sort of thing. I think I'll leave it there for this intro. There's more slides here that I left out, some that I skipped over. So feel free to check out that link. All right, we're going to switch over to the interactive part. So hopefully you're set up with R installed, RStudio installed, and those packages. So what I'm going to do now is switch over my share screen to RStudio, and we can get started. Maybe before I'll do that, I'm not sure if I talked about the schedule for today. Yeah, so in that link, I talked about the half an hour introduction and setup we'll have for the next hour or so, working with some vector data. We'll take a break, a little more vector exploration, and finish up with raster. So we're going into the open and plot vector files right now, I suppose. Yes, I have introduction and setup here because when I do this workshop in person, sometimes it takes half an hour for people to get their machine set up. So I hope that's not the case here. Okay, switching over to RStudio. Okay, hopefully people are seeing an RStudio window right now. And what you're seeing here is I've downloaded the data in that link that I sent people, unzipped that zip file, and what I've done is open the R project file in RStudio. And after that, I've opened basically a starter R file that I've called lesson 1. It doesn't need to be called lesson 1 because I want to put all the code in this file. And the file we're going to be working with first is the Erie outline file. So if I go here to data, you'll see all the data we're going to use for this workshop. We're going to start with a vector data, Erie outline.shape. And this is the interactive part. So I'm going to start live coding as it were, or start typing, and you can type along with me. And if anything comes up, like syntax error, something that seems off, put a question in the chat or Slack, or even unmute yourself. I'm cool with that. All right, we're going to load Erie outline. So what I'm going to do is use the SF package here. First, I'm going to load the SF package. I'm going to highlight these 2 lines, and I'm going to go slow because I have the danger of going too fast. I'm going to highlight those lines and click run. Now there are, of course, keyboard shortcuts in RStudio. You don't need to click run. I'm going to do that. Make sure I go slow. So as I said, we're using the SF package, and the function we need to load data is called st_read. So I'm going to type st_read and the path to the file. Now, if you opened your RStudio with that rproj file, then your path will be the same as mine. I highly encourage that. Otherwise, you might have to search on your computer for it. So the file's in the data folder. It's called Erie outline.shape. I'm going to highlight that line and run it. Just make sure there's no errors. Yep, no errors. This text here that are printed out is expected. Let me make my screen a little bigger. Let me know if it's too big or too small. And what I'm going to do is assign the output of the stread function call there to a variable called stoutline. Run that line again, and now I have an Erie outline object. If you're using RStudio, you'll see that object here on the right side. And what we're going to do here is basically explore this object. Assume that we don't know anything about it other than its name. We can assume that it's an outline of Lake Erie. One thing we can do as a quick check is to check the geometry type. Remember, I talked in my intro slides about the various geometry types, points, lines, and polygons. We'll see what the type of this object is. To do that, I'm going to use the function stGeometryType and run that line, and it tells me that the outline is a polygon. It could have been a line, that makes sense for an outline, but in this case, it's a polygon. Another thing we might be interested in is the projection of this data. Is it projected, unprojected? By that, I mean, is it in units of latitude and longitude, or meters, or the various things, various units that projections can take? So to do that, I'm going to use the function stcrs and type Erie outline. Gives me a lot of information. Previous versions of SF are much cleaner. All right, what do we see here? We see, I apologize, it's kind of messy to interpret, but it's telling us actually not much in this beginning part. It tells us here that it has an EPSG code. That's an important thing to know about. If you search different projections, the most common ones have an EPSG code. So if you're like using a search engine to figure out projections, that's something to know. So what we could do is type in that EPSG code and learn about this projection. But if I scroll further down, we'll see some line that says it's in UTM. That's a very common projection, and it gives you accurate areas at small distances, like the size of Lake Erie. And another thing to note here is that the units of this projection are meters. So that should be an immediate clue. We're dealing with projected data in units of meters, not unprojected data in units of degrees. Next thing you might check out about this object is the extent of the object. So if I check the extent with this function stbbbox, stands for bounding box, and run that line, that's another clue that we're dealing with projected data, because we see here the magnitude of these values are very large, whereas longitude goes from -180 to 180. Here we're dealing with hundreds of thousands. So this is in meters from some origin on the Earth that we could find out if we researched the projection, but we're not going to do that. So from some point on Earth is 0, 0, 0, 0, and this is giving us offsets from that origin.
Jem, there is a question.
Okay.
On the chat. Do all unprojected data have unit of degrees?
Yes. I mean, I could be wrong, but yes. Like WGS 84 is the main latitude and longitude unprojected representation of geospatial data, and it's in units of degrees. Decimal degrees to be specific. All right, final thing we're going to do. I know this is like really drawn out, but final thing we're going to do is plot the data. And now I'm wondering, maybe people don't have this package, the ggplot package installed. but I think that's the nicest way to plot this data. We can, of course, plot the data without ggplot by doing just plot Erie outline. And I think we want to plot just the geometry. So what I did there was type plot, typed Erie outline, $, and then geometry. You'll notice I did a little trick there because I can't help myself. When you type the $, in RStudio, it offers helpful auto completion. So I typed the $, there, and I started typing geometry, and it auto completed it for me. And I can accept the auto completion by hitting tab. Just a little trick in case I do that again. If I run that, it gives me a plot. I don't think it's that nice of a plot, so I like ggplot. Hopefully you have it installed. If not, you can install it with the command install packages. Like this. I already have it installed, so I'm not going to do that. I'll just say now that I will post a link to this script that I'm typing out here in the Slack at the end of the workshop. So if you're furiously taking notes for that purpose to save the script, I'll be posting it. So what I want to do is plot this in ggplot because I think it's a nicer way to do it. And to do that, I'm going to use ggplot syntax that should look very familiar if you know ggplot, like in a non-spatial context, where we start the plot with just an empty ggplot command, and then the plus sign. And then here's where it differs from the non-spatial ggplot context. We're going to add a layer to our plot that's an SF layer with the geom_f command for SF. And we're going to tell it that we're going to plot the Erie outline data. And if we just run that, I first have to load the package. I think it's somewhat nicer. We can make it even nicer by setting some options. So like, I can say that I want the lake filled with a blue color. That might be nice. I could set a darker outline with the size attribute. I can add a title. So I'm going to the end here, hitting a plus sign, and then using the function ggtitle. This is all, the ggtitle bit here is the same as you would do in a non-spatial context with ggplot. And I'm going to title my map ggtitle, or Lake Erie outline rather. And if I run this complete string now, I think that's nicer. And of course, there's much more customization you can do. You can get rid of this gray background. One of my favorite ways to explore geospatial data is with the map view package that you may have seen me load at the very beginning of this script. So if I do map view Erie outline, and run that, it will pop up a representation of our geospatial object that I can pan around on top of this base map. I can zoom in. It's pretty neat and very, very easy in comparison to some other tools. All right, I think that about covers it for this first part. Happy to take any questions. And if you're sitting on questions or need some time to come up with additional questions, I think we'll take a quick break here. I have in our schedule here a 10-minute break until 10 minutes from now. So I'm gonna stop sharing, or turn off my video rather. take a quick break, and I'll be back in 10 minutes. And feel free to put questions in Slack or the chat in the meantime. We'll be back with exploring attributes of vector data.
Okay. In the meantime, I will pause also the recording.
Screen. I'm showing the the file browser in RStudio. And so, for instance, we were working with the Erie outline file, and you notice that there's 4 files here with the Erie outline name. So in order for your shapefile to load, you need all 4 of those files, or at least 3 of them. I don't know. You need multiple files. And I'll just say that GeoPackage solves that issue. You don't need to track or move around multiple files. It's just one.
Thank you.
There's another file or question rather about generating shapefiles. So one way to generate shapefiles is very labor intensive. You take a GPS unit, go out to the field, click some coordinates, georeference them. That would be one way. Yeah, typically I think shapefiles that you would use would be extracted from some larger collection of data. So maybe your country has a GIS portal that has a bunch of very large shapefiles, maybe for the whole country or the province or something. And you would take that larger shapefile and extract a piece of it. I think that's probably more typical. Yeah, manual creation is possible. I wouldn't recommend doing that in R. I would recommend using instead of a programming interface, use a graphical interface, like QGIS is a popular one. There's a question here about how to call geopackages. There's a way to save files as geopackages. So I'll show that real quick, because I didn't show anything about writing files, just reading files. So here, we have our Erie outline file, and let's say we wanted to create a geopackage instead of a shapefile. We would use the command stwrite, and we would type in our object, in this case, Erie outline. And I believe what we could just do is data Erie outline .gpkg for geopackage. I think this will work. Yep, seemed to have worked. And if I go in my file browser here, why don't I see it? Oh, here it is at the bottom. Now there's an Erie outline .gpkg, and it's just a single file. And it works exactly the same as our shapefile. No losing one piece of the shapefile, which was a common problem for me. All right, we answered some questions. I think we're probably moving fast enough to have another break. So there'll be another opportunity for this type of back and forth. We're going to move on to looking at attributes of shapefiles. We're actually going to use a different shapefile for that. If you noticed in the Erie outline object, there was no attributes. So if I just run that, I guess technically there were attributes. There was a single row in our data frame here for Lake Erie, and it did have attributes, but it's just not that interesting. We'll get a single attribute. So the file we're going to use instead is the Erie zones file. So just like we did with Erie outline, let's create an Erie zones variable holding the output of stread. And instead of Erie outline, we're going to do Erie zones. Now these zones, I believe, are like fishing management zones in the lake. So if I run that line, now we have both an Erie outline object and the Erie zones object. And we could do multiple things to explore that object. We could just run Erie zones by itself, and it will print a lot of stuff to the console here. Another thing we can do is use something that is best used in RStudio, but it's the view command. So I can view area zones. And it will pop up a separate tab here that for some reason is not loading. Oh, there we go. Just takes a minute. That can be a nice way to explore the data, maybe in a more readable format than just in the console. So we see that there's 11 rows to this object, or I suppose 11 management zones. In Lake Erie, we've got the size of zones and various units. And we can distinguish that we have an SF object, partly because it has a geometry column. So if you're familiar with non-spatial R programming, you've no doubt used data frames. Here, area zones is a data frame, but it's got this geometry column, and that's what SF focuses on for its plotting. Yeah, so we can tell all sorts of things from view. We can tell the number of columns. We can tell the column names here. We might want to do operations on the column names, so it's useful to know that you can print the names of the data frame with the names function. So if I type names, open parentheses, area zones, close parentheses, and run that, it will give me the column names of my object as a vector. So we can do things like rename the names, let's say. Let's do one more exploratory thing. It's useful to know. It's just, you can look at the first few lines of an object with the head function.
Jem, there is a question.
Yep.
From Rebecca, do you know if geodatabase files are something compatible with viewing?
Yes, they are. I think it just requires an extra argument. So here you would say, let's just assume area zones was a geodatabase. You would have like area zones.gdb, and then you type whatever layer you're interested in. Might be zones, might be something else. I think that's all that's needed. I've done it before, but not in a while. Hopefully that answers the question. If you try it out during the break and it doesn't work, maybe we could debug it together. Okay, let's explore some of the column types here. So one thing we might want to do is like subset the data frame. If we look, I'm going to switch over to the view tab. I don't know why it's not going. There we go. Just takes a minute for some reason. Switch over to the view tab. Again, you can get to that same place by typing view area zones in case you've closed it. And just for exploratory purposes, let's say we're interested in a specific management unit. Let's say management unit 5. So what I did here was in my view tab, clicked management unit to sort the data frame by management unit. If I scroll down, it says that there's 2 rows in management unit 5. What if we, for some reason, wanted to extract and plot and do operations on just zone 5? How would we do that? So it's actually very similar to what you do in non-spatial operations. And we're going to use the dplyr package. This is just extremely popular for non-spatial operations, and it works with spatial operations. And I think it's very readable and easy. There's multiple ways to do the subsetting. This is just one. So the function I'm going to use from dplyr is called filter. So I'm going to type the package name dplyr : filter. And the reason for this is that in base R, So like not in any package, there's a function called filter. So you can have problems in your code if you just call filter. Like if I did library dplyr, we'll see that, yeah, it'll pop up with a bunch of messages. R is complaining that in base R there's a function called filter, and in dplyr there's also a function called filter. So we can avoid that mess by using the colon syntax. And what this says is it says use the filter function from dplyr, not from base R or anywhere else. So we're going to filter our Erie zones object. And we want just management 5. So I'm going to type Erie zones management unit. And we want just the ones that are equal to management unit 5. If I run that, we'll see that indeed we got just 2 rows. That's the same thing we saw when we viewed it in the view tab. So that seems correct. Our management units are management unit 5. So we can assign that to an object. Let's call it zone 5. And run our line again. And now in our environment pane here, in our studio, we should see an object called zone 5 with 2 rows. Now let's plot our zone 5, and I guess Erie zones as a whole. So since I think it's easiest, let's start out with the map view package. So let's do map view Erie zones. And if we just run that, we'll see this very neat looking map of all the fishing management zones in Lake Erie. And we can like click on the individual polygons here and get the attributes. So that's pretty cool. Another thing we can do that I haven't showed yet is combine map view layers. So we can have a map view layer of all the zones, and then we can have a map view layer of just zone 5. So if I run that, it will create a layer Erie zones, and on top of it, a layer for zone 5. Now if I run that, you can see, oh, zone 5 here is on the right, on the eastern portion of the lake. We can do some coloring as well. I think the argument is color. Yeah, so color gives us the outline. Maybe we want fill. Nope, that's not it. So here's a good thing to do if you get stuck, like I am currently, is you can look up the help file for our function using the question mark command. So if I do question mark map view and run that, we can scroll down and find map view here. Click it and we can read all about the function map view, all the arguments to map view. Now map view is a very complex function. So you can see the help file is very complex as well. One thing that's nice about RStudio is it has this search bar. So I could type color here, and I'm just going to hit enter to scroll through all the instances of color. Anyway, let's not get too distracted here. At the next break, maybe I'll be able to figure it out with without this big detour. In the meantime, let's do a ggplot of this data. If you recall, the ggplot syntax is the ggplot function by itself, then the plus sign, then we add a spatial layer with geom_sf, and we point it at data equals zone 5. And if I run those 2 lines, we'll get a map showing, yes, it's the 2 rightmost or easternmost zones in the lake are zone 5.
Jem, there is a question from Carolina. Which layer are you using to check in the viewer window? It looks different to me on my RStudio.
Which layer?
Yeah, are you using to check in the viewer window?
I'm not sure I understand. So we can run just the area zones object and display that in the viewer window. If I highlight it and click run here, it will show the entire thing. So I guess the layer is area zones. We can also do we can also do zone 5 by itself. Highlight zone 5, click run. Hopefully that answered the question. Any more detail would help. All right, let's say we wanted to plot, instead of just zone 5, we wanted to plot all the area zones. We wanted to plot them by management unit. I always recommend going to map view first. So we can do map view area zones and tell it that we want it to color by management unit. MGMT unit. If we run that, we get this very nice looking map where each of the 5 management units are colored in a different color. We can do a similar thing with ggplot. So ggplot syntax is ggplot by itself, and then a layer geom_sf pointed at, again, the entire object, area zones. And this is getting into more complex ggplot syntax, but you specify colors with this AES function. And you say that you want to color by management unit without quotes. If I run that, it'll give me a similar, I think less nice looking plot of the management units color coded. Oh, but this kind of static plot would be something you might put like in a paper or presentation. And then of course you can clean up the map. So you could get rid of this gray background. You could make a nice title. I won't spend a lot of time on that. I guess it's not too much. Might as well go ahead. So we can add a title with GG title. So we can say, this is a map of management units. And we can add a subtitle to that. Subtitle equals colored by zone. what else can we add? We could change it so instead of saying management unit in all caps like this, we can give it a nicer legend title with the labs function. And we can say that the color in the legend, we want to call it unit ID. Much nicer capitalization. If I run that complete bit, we have a nicer looking map. I think so. I guess one last bit of plotting, and that's dealing with lines. So far, we've colored the zones, and this might not make much sense for polygon data, but for line data, it can be useful to adjust the line width in your plot. So let's just, I guess, practice with this polygon data, even though it doesn't make as much sense as it does with line data. So let's make a new ggplot. It's exactly the same as above. So actually, as a shortcut, rather than typing it all, I'm going to highlight that line up there, copy it, and paste it. The one thing we're going to change, though, is where it says color equals mg/mt unit. We're also going to vary the size by that. So if I run this line, let's see what it gives us. It will give us a warning saying that mg/mt unit is like not a number. It wants us to use a number for line widths and not the character values that make up the management units. So we can fix that by adding a call to the scale size manual function and defining values for that function in a vector. And we want the vector to be the same length as the number of unique management units. So we want 5 numbers. They could be whatever we want. I mean, one easy thing to do is like 1 through 5. One through 5 separated by commas. So now if I run that complete bit, see, now I'm getting an error saying argument values is missing. It's because I misspelled value here. I wanted values, not value. Now it runs well with no errors. And we could adjust this whatever we want. Let's say like 5 is a little too big. Maybe we want zone 5 to also be 1. Run that whole bit again. Now 5 is a more reasonable size. Just useful to know that we can color spatial objects and also adjust the size of their outline. I think that about covers it for our exploration of vector attributes and plotting of vector attributes.
Great, Jem. There is a kind of question on the chat.
Okay.
Rui said that for some reason my map view is not showing early outline or early zones on the map. Not sure what is going on. Tried restyling map view, but I still can't view the shapefile in the viewer.
Yeah, I mean, that's surprising. It's surprising. I would think that you would get some warnings before you got to that point. Like if you installed the package, you would get warnings on install. That's what I would expect. Another possibility is Yeah, I don't know why outlines wouldn't. I can explain why like the base map wouldn't load, but the outlines themselves.
Yeah, for me, like the base map is still showing up, but whenever I try to load the outlines, it just shows a blank base map.
Where is the base map located in the correct spot at least?
Yes, like it shows Lake Erie, but it doesn't show any of the additional layers.
Huh. Does the ggplotting work?
Yes.
Huh. Yeah, I would think there would be an error with the map view installation in that case, or some error, like it wouldn't be just silent.
Yeah, I'm wondering if it's like trying to install an earlier version of map view or something, but that doesn't seem like likely.
Yeah, I mean, yeah, my only thought was that computer was missing some system software. A lot of this geospatial stuff requires that, like if you're on Mac, I know there can be issues
Oh, I
not
am
having
on
that.
that. Yeah.
Like with Windows, what they've done is bundle all this system stuff like with the R package installation. So you download it and you get everything you need. I think Mac might require some configuration. So why don't I put a link in the chat that you might use to like check if you have the required software.
Okay, that'd be awesome. Thank you.
Okay, I'm looking at our schedule here, and I had 2 more sections planned for today. We could do an additional if we have time. Just trying to decide when to take a break here. Let's do one more and then take a break before we get to the raster sections. So the next section is on, let's say you don't have a shapefile. Let's say you have point coordinates, like maybe you went out to your study site with a GPS unit and collected some coordinates and you want to show those on a map. So the scenario we're in is you have coordinates already. They're in a CSV file, comma separated value file, and you want to put them in your map. And the file we're going to use for this is called fishtracks.csv. So someone, not me, went out and I think tagged some fish with like radio transponders and measured the locations of the fish. So our objective is to create a map of fish tracking locations, and we want to show this on our Erie map. So to do that, I'm going to load in our fish tracks file with the read.csv function. And our file is located at data/fishtracks.csv. And I'm going to assign that to a variable fish_tracks. Run that, no errors, that's good. We can check out like the contents of this file. One way that I favor is just the view function, similar to what we do with Erie zones. So that's view with an uppercase V, fish tracks. If I run that, you can see what do we have here? 6 columns, 1,300 entries, that's quite a bit. Animal ID here, that must be each fish that's individually tracked. We've got coordinates here, X coordinates and Y coordinates. And another thing they've helpfully included in this file is some projection information. It's telling us that these coordinates here are not latitude and longitude, which we can guess from just the magnitudes of the numbers. But it's also telling us that these numbers are relative to UTM zone 17. That's helpful information. And our objective is to get this data out of CSV and X and Y and into an SF spatial object that's projected into UTM zone 17. One thing that's might be the case in a lot of projects, it's the case here. The data we have in our CSV is projected in the same coordinate system as our shapefile. So we can check that out with the stcrs function. So if we load, again, let's do the Erie outline object. If we look at the projection of the Erie outline object and scroll through this big mess that it outputs, we can see that the Erie outline object is in UTM zone 17. So that's very helpful. That means we can basically do a shortcut. We don't have to assign the projection manually. We can more or less steal it from this object. Before we get there, or I guess it's not before we get there, what we want to do now is instead of loading the data with read CSV, let's take that variable that we assigned, the fish tracks variable, and make it spatial, make it an SF object. We're going to do that with the st as SF function. And we're going to pass to the first argument the fish tracks object. And we're going to say that the coordinates of the fish track object are x first, always x first, and y second. And we're going to tell it that the projection of this data, or otherwise known as the CRS, is the same as the CRS of Erie outline. And we're going to do that by assigning to the CRS argument the output of stcrs Erie outline. And before I run that, let's just put an assignment at the beginning here. Let's assign it to a variable called fish locations. I realize that was kind of a mouthful to type. So I'll kind of pause here after running it. We didn't get any errors, so that's good. I guess a common cause of errors at this step might be misspelling or missing a bracket or something like that, given how complex that was to type. We can check the projection of that object with stcrs. Let's just inspect it to see if it's actually zone 17, if we were successful. I mean, we didn't get any errors, so it's unlikely, but nevertheless, pasted it here, scrolled up through this big mess, and we see here UTM zone 17. So that's good. We shouldn't have any projection errors or projection mismatches. Just like before, let's do, in my opinion, the easiest possible visualization with the map view package. So map view fish locations. Feel bad for the people that couldn't get map view to work, but for the rest of us, we can see a nice output of our fish locations. It's just in the western part of the lake. It's a lot of measurements, 1,300 measurements of the position of several fish. This is kind of going off script, but just for curiosity's sake, I want to know like how many fish are there. So I'm going to use a function, the table function, and give it fish locations and the animal ID. So if I run that line, it says that, wow, those 1,300 observations are just 2 fish. So that's really something.
Again, there is a question on the chat.
Yep.
From Yorit. If fish location would be in a different projection, say Mercator, would map view SF place the dots in the right spot given that it would know both projections?
Now, if you ask me this question like 5 years ago, the answer would be no. It used to not be smart enough to figure that out. Now it is. So yes, it would figure that out and place them in the correct spot. Assuming that the data is actually correct. Like, so when I created my STSF object here, if I said that CRS here was something else, like some random EPSG code, I'm not even sure if that's a valid code, but yeah, there's no CRS there. Anyway, if you like misassign CRS entirely, it wouldn't work. So if you had 2 layers with correct CRS information, it would line up. Hopefully that subtlety I made clear. So see, I showed map view here. I mean, we can do the same thing with ggplot. I'll go a little faster through the syntax here because we've seen it so many times. Using the geom_sf layer, pointing it at fish locations. And running that, we get, I don't know, not that nice of a plot. We can do the map view layers trick. So I could do map view, what is it, Erie outline, and add a fish locations layer. Huh. Well, you just asked me if they would line up, and now they're not. Oh, maybe because of this stuff I did. There we go. Okay. Oh, that fixed that problem. Yeah, so now we can see the fish locations plotted on top of the outline map. And I can like click on these individual points and see, I guess, the animal ID. Let's just for fun, plot the points by the animal ID. See where these fish went. Okay, it looks like the yellow fish, starting with 28, stayed to the north of the lake, and the purple fish went to the south. I think that's just about it for the CSV portion. I guess one thing I might point out is talking about the CRS here, like having your data in projected coordinates, I don't know, it's kind of rare in my experience. So a good EPSG or CRS code to know is 4326. That's the EPSG code for just like latitude and longitude. So let's say you had, say fish tracks was not in UTM 17, it was in latitude and longitude. What we would do is, instead of assigning the CRS from the Erie outline, we would type 4326, and this would give us an SF object in latitude and longitude in units of degrees. Okay, so I guess similar to last break, feel free to ask questions and I'll address them when we get back from the break. Let's have a slightly longer break, maybe 15 minutes. So maybe just before 15 minutes, so I'll log back in and look for questions. We'll pick back up with raster data after then.
Okay, great, thank you. I will pause the recording.
See if there's any questions. See if there's any questions. Nope, I think we covered them all. I think before we move on to raster, during the break, I was thinking maybe I would show people this really helpful website. epsg.io. And this website has those EPSG codes, and you can look them up and learn more about individual ones. So like I was saying, 4326 is the common latitude and longitude unprojected EPSG code. So if I search that, I can learn all about the EPSG 4326. It's very common. We can look up like what is the EPSG code for UTM 17 North. Probably want to use this one, North America, not South America, if we're in Lake Erie. It's telling us that the EPSG code is 26917, so we could have put that in instead of stealing from another object. One other thing I thought I'd mention before we go to rasters is just the wealth of operations that the SF package has on vector objects. So we did some subsetting with dplyr, plotting, exploration. This is an intro workshop. I didn't really cover like GIS operations, but SF has a ton of them, basically all of them. So if you want to buffer like your fish points or your lake, there's operations to buffer. You could find the center of the lake. I mean, this list here on the SF website has a whole list of them. It's got like tutorial walkthroughs for doing things like plotting, more advanced GIS manipulation. So check that out. Because we're going to raster now. The data we're interested in is a TIFF file. It should be in here. Yes. Erie bathymetry or eriebathy.tiff. First thing we're going to do is load the necessary packages to work with raster data. So SF works with vector data, not raster data. The package to work with raster data is called raster. So we're going to load raster. We're also going to load a package called rgdal. GDAL and the interface to GDAL, rgdal, will tell us things about projections, and they're specific to raster data for the most part, these days anyway. I'm going to run those, load those libraries, and it's going to give me a bunch of output. This is the kind of output that might be of interest to the people that are having trouble with map view. Like, it will tell me the versions of the system software I have. So you can look for problems. Perhaps there's like a warning when you load these packages that would be informative. First thing we're going to do is look at the, get a summary of our geotiff file, eriebathy.tiff. We're going to do that with the gdal info function, which is from the rgdal package. And I'm going to type in the path to that file. So in the data folder, eriebathy.tiff. And run that line, and it's going to give me a bunch of output. Remember I said in the intro how raster files are essentially grids, and each cell within that grid holds a value. So we can see the dimensions of our grid here. It has 620 or so rows and about 1,800 columns. Grids are not always, like the dimensions of each grid cell are not always square. So we can see here that the dimensions of our grid are not square. The X dimension is slightly shorter than the Y dimension. And we can tell that these numbers here are in units of meters because it prints out our projection here. It's in UTM zone 17, like all our vector data, and it tells us that our units are in meters. So each X cell is 276 meters wide and 370 meters tall. I don't think there's much else interesting to see here. I mean, you could ignore these warnings.
Jem, I have a question.
Go ahead.
I see that you already downloaded the area bathymetry GOT file. And let's say if you didn't download it before and you want to download it directly from R, can you little bit talk about that? Like, is there any possibility that you can download the data from the cloud or from the website that the data is stored and process it directly?
I'm not sure about that.
Okay.
I mean, it seems reasonable and likely that it would. One thing we can do is check the help file for the function that loads raster data. So if I do $raster, yep, it will show the help file for loading a raster into R. So if we look at the first argument here, X, it says it can be a file name. Doesn't say it can be a like a URL on internet path. So from the help file, I would guess no. Let's look at the examples here. Sometimes they have no. Seems like the answer is no.
Okay, great. Thank you.
All right, so we checked out the projection, the dimensions of our data. I mean, one thing we might do, I just showed the help file for the raster function. Let's actually use that. Let's load the Erie Bathy file to a variable called Erie Bathy with the raster function and give it the path. So if I run that, again, you can ignore these warning messages. One thing we might want to do is look at the so far we've looked just at the dimensions of the grid, but what about the contents of the grid? So we can do things like look at a summary of the Erie Bathy object, and it'll give you a summary of the contents. So it says that there's a lot of missing data. The median, I think this is elevation, is 63. So it looks like a lot of our raster data is like outside the lake. And then a small amount is inside the lake and it has a maximum depth of 62 meters, I suppose. But one tricky thing to know is that when we looked at the projection information and it told us the raster was units of meters, that is just the spatial location. So we know that the cells are whatever, 270 meters high, but that says nothing about the contents of the raster. So these numbers here could be anything. I just assume they're meters, but we don't know. We would have to look at the metadata for this file, the source of where we got it. Let's make a plot of this. we can, just as always, use the map view package to get the simplest possible and easiest solution here. Map view runs on vector. It also runs on raster. So if I feed Erie Bathy to the map view function, it will show me our beautiful bathymetry / elevation. Yes, just that. Go ahead.
There is a question. Stephen has some issue to create a raster layer object from the file. Stephen, can you unmute?
Yeah, it's an error. It says cannot create a raster layer object from this file.
Do you have the path correct? Did you mistype? I mean, that would be my guess.
Yeah, I've checked that a few times. Yeah, I even copied and pasted it. All right, I'll figure it out.
Yeah, I mean, it seems like either a data path issue or an underlying software issue. So like I was telling the people before, like the SF package and the raster package are just, there's sometimes called wrappers. Like there's some underlying software that the SF and raster package are using to do this. And so like on Windows, that all gets installed for you when you install a package. But on like Mac and Linux, you have to install those separately. So that can be a source of errors. That's my recommendation. All right, as I was saying, it looks like most of our raster is outside the lake. And it's like I suspected, where it's actually elevation, not bathymetry. So we've got positive numbers are outside the lake and high up, and negative numbers are inside the lake and at depth. So map view is one option for plotting. Seem to have skipped place here. I'll fix this later. We can also use the raster package to plot. It's not as nice. We get something that looks like this. We can use ggplot to plot as well. That's my favored static plot method. So we start just like we did with the vector, open call to ggplot +sign. But this time, instead of geom_sf, we're going to do geom_raster. And we're going to say the data is not Erie Bathy by itself, but we actually need to make a data frame of Erie Bathy. Actually, before I get to that point, I'm going to go in the console here and use the class function to just show you that the Erie Bathy object is of class raster layer, not of class data frame. And ggplot operates only on data frames. So I guess I got a little bit ahead of myself. Let's create an Erie Bathy data frame. So what it's going to do is pull out the grid cell values and put them like in a, I guess, data frame. I don't know how else to say it, a table where one column is the grid cell value, one column is X, one column is Y. You have 3 columns. It's a nice data frame. Well, I'll show it with view after we make it. We're going to use the function as data frame. And we're turning Erie Bathy into the data frame. So we'll put that as the first argument. And we need to say that XY equals true. That will give us those coordinates. Ran that line, no errors, so that's a good sign. I'm going to view that object with the view function. If I view Erie Bathy, it's like I was saying, you have the X coordinate, the Y coordinate, and whatever the grid cell value is. And it just so happens that I think this starts in the top left, but the top left are missing values. That's why we have NA. Anyway, that's good. We've created our Erie Bathy object. And now here in our call to Geom Raster, we can feed it Erie Bathy. And we need to use that AES function that we used for the coloring and the line width, but we need to specify the columns here. So the X column is X, Y column is Y. That's pretty straightforward. And the last argument we need to give to AES is the fill argument. So how is it going to color the grid cells? And we want it to color by the Erie Bathy column. If you recall, when we viewed Erie Bathy, there were 3 columns, X, Y, and Erie Bathy. So here we have them. So if I run that, it's going to think for a while and give us, looks kind of distorted, but I don't know, maybe not that great of a map. We can improve it by changing the color scheme. Light blue to dark blue isn't the greatest. One color scheme I favor is the Viridis color scale. So we can change the color scale by adding a plus sign to the end of our call and start typing scale fill Viridis. And we want these letters here stand for D for discrete, C for continuous, B for, I don't know, binary maybe. Anyway, we want C for continuous. Our depth / elevation data is continuous. And that's it. So if I highlight that whole section and run it, we get a nicer looking map. I mean, I would adjust this plotting window to stretch it. And if I were to like save this plot for a publication, I could specify the like dimensions so that this stretching looks good. Let's explore the values of our raster some more. We looked at the summary of the raster, but we can pull out the like individual values. Like we can pull out the minimum or like the deepest point in the lake with this function min value from the raster package. So if I feed min value the Erie Bathy object and run it, oh, I see what I did. Here, I reassigned Erie Bathy to a data frame, and the min value function operates on raster objects, not data frame objects. So what I'm going to do here is actually scroll back up in my script and reassign Erie Bathy to a raster object. So this line here, where I assign Erie Bathy to the output of raster, I'm going to run that again. Again, ignoring the warning. And running min value, there we go. Now no error. And again, we see that the maximum depth of the lake is 62 meters, we guess. We can do a similar thing. I mean, you might guess that in addition to min value, there's a max value. And this will give us what the height of those hills to the southeast of the lake. 600 meters. Kind of less interesting than the depth of that. Something we could look at maybe is the missing values next. You may have an interest, for example, when you're creating plots or when you're doing analysis, like either recoloring the missing values or clipping the missing values or even replacing and filling the missing values. Let's talk about those some. You can kind of see that on the outline of our plot, this dark gray. So why don't we actually reuse our, kind of lost my place here. Reuse our ggplot code here, where we plotted the raster object. And actually, I know this might cause some confusion, but I'm actually going to rename this Erie Bathy data frame object as Erie Bathy _df for data frame. Hopefully I don't lose people, but this will make it simpler if I assign Erie Bathy df and then replace the call to Erie Bathy with Erie Bathy df in my ggplot call. And in this case, instead of just the empty scale fill viridis, what I'm going to do is set the NA value. And I'm going to set the NA value. We could set it to whatever we want, but I'm going to set it to deep pink. That's very noticeable. Hit run, and wow, now you can really see the missing values. Now, of course, there's functions in the raster package that I won't go over now where we could set the missing values. There's a lot of instances where you might want the missing value to be set to 0, for instance, that sort of thing. Similar to the SF package, the raster package also has an extensive like help file with tutorials and that sort of thing. Let's make plots of the bathymetry now. Instead of a map, let's make a plot of the bathymetry, maybe a histogram of the bathymetry. That might be good. So let's use the ggplot tool, empty call the ggplot, and this time instead of geom_raster or geom_sf, let's use geom_histogram. And let's feed it data equals Erie Bathy df, because remember ggplot operates on data frames and not raster objects. And let's tell it that we want to make a histogram of not the x and y's, but the actual depth / elevation values. So AES Erie Bathy. And this refers not to the Erie Bathy object, but the Erie Bathy column. If I highlight those 2 lines and run them. Success, we have a histogram of the bathymetry of our data set here. And we see that what most of the map is at 0. You have those hills to what the southeast, and then a little bit less than 0. Pretty shallow lake for the most part. I think that about covers what I have prepared for our explorations of raster data. Let's see what else I could talk about. I can talk about cropping rasters or extracting values from rasters. Okay, let's do cropping first. this is the last section I had planned for today.
Actually, on the chat, people were in favor of extracting value, but yeah, if
Okay,
we can do both, it would be great.
maybe I'll start with the extracting. It's a little, honestly, it's a little bit simpler to do the extracting. So let's extract the depth underneath our fish tracks. So for this, we're going to use the area bathy object we already have in our working environment here, and the fish tracks object that we already have. So let's create a new object called fish tracks bathy for bathymetry, and use a function from the raster package called extract. And we're going to tell it that we want to extract from the bathymetry object. So X is what we're extracting from, and Y we're extracting to. I don't know. We're extracting fish locations, and this is a bit tricky. I mean, let's try it. Fish tracks. And tell it that we want to return a data frame and not, I guess if you don't do this, it gives you a raster back. No, didn't work. Okay, so what we need to do is convert our fish tracks file. This is getting, I don't know, a little bit off track, or it's a little bit difficult to explain, but fish tracks, if you recall, was an SF object. And we need to give it a different kind of object, an SP object. So to convert an SF to an SP object, you need this line here, where you're saying fish tracks, please convert to a spatial with the as function. I know this is a little bit like, I don't know, magic words or something, but that's what we're going to do, and we're going to hope it works. Doesn't work. This is very helpful to see the debugging, I think. It's telling us that fish tracks is a data frame, and we expect it to be an SF object. So I'm going to go down to the console here and see what class our fish, it's a data frame. I'm going to scroll up here and see what was going on with fish tracks. Oh, we didn't, that's confusing. So fish tracks was our data frame, fish locations was our SF object. Why I did that? Who knows? So I scrolled back down, hopefully that wasn't too fast. We want to extract not fish tracks, but fish locations. Terrible naming. So I run that, there we go. Now no error. And what I'm going to do is view the output of that rather than print it, because I think it's going to be pretty long. So if I view this, I see, I don't think these IDs mean anything. I think that they're just like in order. And we have all the numbers that underlie one of the fish tracks. Let's get a summary of that. So let's do the summary function and look at fish tracks bathy. And let's look at the column area bathy. This will give us the, what, like median and extremes of that column. So it looks like they went, or they were over a location that was as deep as 21 meters, we guess. Kind of odd that showing that fish went up on land. 2 meters up, so who knows? Maybe 0 is not like lake level. It's very possible. That's basically it for extraction. I mean, as far as GIS operations go, it's a really powerful one with not much like lines of code here. Yeah, so just the possibilities are endless. If you think maybe you don't have fish tracks, maybe you have something, maybe you have like buoy locations and you're getting air temperature. I could see that. Going with the GLEON theme. We can make a plot of this. I mean, one thing I'd like to see is these positive numbers. So let's make a ggplot object, and we'll do geom histogram like we did before. Tell it to operate on fish tracks bathy. And tell it that we want to look at the Erie bathy column of that object, not the ID column. Yeah, so a lot of interesting insight from this graph here. We see that they hung around a lot of locations that were 10 meters or so. And then this odd spike at 20 meters, but almost like they were following depth contour lines, huh? All right, I think that's about it for the extraction. Happy to answer any questions about extraction.
I'm actually just getting an error when I throw the extraction. So I was wondering if I could post the code in the chat and see if I've misspelled anything or something like that.
Go for it.
Okay. If not, it might be an issue with my fish locations earlier on in the script, so I'll have to look over it. But
Yep, fish tracks versus fish locations. That could totally be it. Sorry for the confusion.
no worries. Thank you.
All right, I'll finish up here with some cropping. Let's say we wanted to reduce the amount of our elevation bathymetry raster that was outside the lake. We wanted a more tight crop to the lake bounding blocks. To do that, we would use the crop function. And we would give it the X argument Erie bathy. And we would say we want to extract from the Erie outline object. You think way back to when we use the outline object. And we're going to have to do a similar thing we did with extract. We're going to have to convert the Erie outline object to a spatial object instead of an SF object. The SF package and the raster package were not made by the same people. It's basically the explanation there. And we're going to assign the output to a new variable called Erie bathy cropped. No errors there, so that's good. We can map view Erie bathy cropped. I'm going to, in the autocomplete here, I'm going to hit the down arrow to select Erie bathy cropped and then tab to actually select it. Saves me some typing. And run it, again, ignoring all those errors. And it might be a little bit subtle, but we did get a smaller area returned here. So one thing we could do is map view them both, I suppose. So let's map view Erie Baffy, and then add as a layer the cropped layer and run them both. Yep, so this is a good view of it. There are original data is in this sort of lighter color that extends well beyond the lake. And then the crop data is nice and fitted to the lake itself. You could definitely do similar operations. Like one thing we could do is like crop the bathymetry of the zones, for example. That's something we could do instead of the outline of the entire lake. Yeah, I mean, I guess I'll leave it there. That's really all the material I had prepared for today. Maybe I'll leave you with some resources. So I already showed the SF package website, which I'll put on Slack as well after the workshop. I could show the Raster package website. So it's rspatial.org/raster. And I'm going to click here where it says the Raster package, and it will give me all kinds of things we could do that I didn't cover. So we could do things like we could do calculations on the raster. We could add rasters together. We could do kind of what I showed in the intro slides, where I had some vector data plotted right next to a raster grid. You could convert between the two. Rasterizing and vectorizing is what those operations are called. So yeah, this website has a lot of things. I mean, I haven't really found something that I couldn't do here with the raster package. It's not always the fastest, but I think it's readable. Not as complex as some other systems. Well, one thing I might show is the data carpentry website that I have here. So these materials were all adapted from the data carpentry materials, which are focused on not lake data, but they use data from Neon, if you've heard of that. So not GLEON, but Neon. So maybe you're a big fan of Neon data, or just want to review more materials. You could check out the Geospatial data carpentry materials. So the materials I showed today were adapted from this Introduction to Geospatial Raster and Vector Data with R. And if I go to the website here, there's a whole walkthrough of things I didn't cover. I didn't cover like raster time series. I just showed a raster as one layer. You could have a whole stack of rasters and do operations like, I don't know, temperature through time above your buoys, that sort of thing. What else didn't I cover? Multi-band rasters. So if you work with remote sensing data, a lot of those have multi-band raster data. I didn't cover that. I didn't cover reprojecting data. So there was a question earlier, if you have two different objects with different projections and you try to plot them, will R just sort of figure it out? And the answer is yes, for plotting. Not so much for like doing calculations. So it can be useful to basically align the rasters, reproject rasters or reproject vector data. I didn't show that. So this data carpentry material shows you how to do that if you're interested. There's a question in the chat about, do you prefer working with rasters and vectors in R compared to ArcGIS? I actually haven't used ArcGIS in a long time. I use R, and I also use Python for geospatial operations. And then if I need a graphical interface, like for like editing data or yeah, mostly editing data, I would use QGIS, which is comparable to ArcGIS. But I think the use cases are somewhat different. So like if I'm doing calculations or if I'm building like a data pipeline, I'll do that in R and Python. If I want to like scroll around, if I want to edit data in particular, I'll use a graphical interface like QGIS or ArcGIS. Yep, I think we're just about wrapped up here. I guess before I go, I'll just say, if you're interested in this topic, particularly if you're interested in helping out with data carpentry, we're always looking for maintainers of these materials. We have a whole number of people listed here. Maybe half of them are active, so we'd love to have more maintainers join us. What that mostly means is tracking the GitHub repository where the source for these materials are, and like basically when people propose edits, you check out the edits to make sure they're okay and accept the edits. Basically, it's your role as a maintainer. If you're interested in teaching workshops, I encourage you to become a data carpentry instructor. In non-pandemic times, it used to be that if you signed up to teach a workshop, data carpentry would fly you out to wherever the workshop was. So it was a nice place, a nice way to like expand your professional network. Hopefully we'll return to that someday. There's a question in the chat about how long have you been working with this stuff? Let's see. Myself, it's been quite a while. I think I was using ArcGIS exclusively in like 2012. And then I was doing a lot of repetitive operations in ArcGIS, like doing the model builder stuff where you just have to click through like endless menus. And it was just a lot more efficient to go the programming route. And I initially tried the, what is it, ArcPy in ArcGIS, but I was already using R for some of the ecology work I was doing. And they were just sort of developing the packages at that time. So I kind of switched over. I was involved in a workshop to produce the workshop materials. I know kind of meta in like 2015, actually at the NEON headquarters. That's why all these materials use NEON data. We came up with these lessons and I've been maintaining them and using R for spatial stuff ever since. Okay, well, I'll leave it at that. Post some resources and links in the chat, and hope it was useful.
Great. Thank you very much, Jem. I am going to stop the recording now.